Good evening, everyone. Thanks for joining today evening, taking your time. And no, I'm sure you're going to have an exciting, insightful session today by Amit. So let's get started. Some couple of ground rules. So take the advantage of networking opportunity using chat. You can introduce yourself and get to know each other. You'll have a lot of discussion that can happen through chat window. Post all your questions using Q&A button. They'll be answered during the session by the presenter. In case if at all, if it not during the presentation, but we'll make sure that it get answered at the end of the session. And the information about PDUs will be auto-credited to all the valid PMI credential holders, provided your PMI membership ID has been shared while registering. Correct PMI membership ID has been shared while registering. So with that, Amit, are we ready?
Yeah, let's get started.
Yes. So yeah. So today's topic is quantum computing for project managers. How quantum computing can be used by project managers. So a brief about Amit. Amit is a co-founder for AIM and ML startup called AI Edge Technologies. AI Edge provides AI ML analytics and cloud stack solution to enterprises in financial and healthcare domains. In the past, Amit has led the cloud vertical of an RBI subsidiary organization. He has also worked in companies like TCS, Global Logistics, software provider company across multiple other software provider companies across multiple cities. Amit are mostly into the Hyderabad. Okay, and he has done his BTech from IIT Kharagpur and MBA from IIT Kolkata. He is an very much enthusiast about quantum computing. I'm sure this is very short about his experience and his expertise related to quantum computing. And you will be knowing more about his research and also his details related to quantum computing in the coming up presentation. With that, Amit, over to you.
Thanks a lot, Praveen, for all the kind words. So let's get started. Let me share my screen.
Yes. You are able to share screen. You have presenter pre-roll. Okay, we can see it.
Okay, can you all see my screen?
It's coming up. Yes, yes.
Okay, excellent. So we are going to talk about quantum computing in a introductory way, knowing that many of you are from diverse background, and not all of you may be from technology background. And also, quantum computing is a very new emerging technology, and there are a lot of complexity and depth around it. So our goal is to just introduce quantum computing to all of you, just to light a small spark so that you get thinking about it. So let's start with typical problem. Can we solve using quantum computing? So one example, there are many examples. One example which I have picked up is called ship loading problem. So what happens is if you have containers, so you can see in the middle there are 3 containers. You can have multiple containers. There's an example of 10 containers with different weights. So 1, 5, 9, 21, 35 are weights of 10 containers. And the problem we want containers on 2 ships, and we want to stack those containers in a way that both ships are not overloaded, neither underloaded. So this is a problem which is an example. It's a very trivial example to demonstrate quantum computing can problem. So what if there are 10 rotations possible? So a very quick back of the envelope calculation will tell that if we assume 5 containers going in each ship, then also we have 30,000
Hey, Amit.
or there is a problem.
Yeah, Amit, your audio is problem. Yeah.
Okay, so let me switch off my video. Maybe that will help.
Okay. Yeah.
Give me a second. Have you switched off my video?
Yeah, video is off. Yeah, video is off.
Okay, great. Is my voice better?
Bit okay. Let's continue. We'll see. I'll notify you in case if there is any problem.
Okay, let's continue and then we'll see. Sure.
Yeah.
So let me just quickly
No, it's again started breaking,
repeat.
Amit.
Amit, I can still see you on video.
Because it's video.
Yeah, now your video is switched off.
Okay, you can still. Okay. And
You are
is
back on.
my voice is still breaking?
Yes, and I can see you as well.
Second.
Yes, now your video is off, Amit. You can try now.
And I don't think I switched it off.
Again back, yeah.
Yeah. Let me stop showing and stop video. Okay, let me share again. Can you all see me
No,
and hear me?
we can hear you. I think for now it is good, Amit. You can go ahead and start.
Okay, fine.
Yeah.
All right, sure. So sorry about that, people. So let me repeat last few things which I. So I result a very simple example to demonstrate how quantum computing can be used to solve a practical problem. So we are taking example of ship loading, where there are a couple of ships which are to be loaded with 10 containers, and weights of each container is given to us. And we need to determine load those two ships with those 10 containers. There are too many available ways for this simple example, and more practical, more than almost 15,000 containers.
Amit, still it is much breaking and shaking. I don't.
Mhm. Okay, let me change my connection. Give me a second.
Yeah, Guru Raj will ask him to start from the beginning. No worries. Wait.
Hi, Praveen. Is this better?
Yes, much better. Much better.
Much better. Okay. Okay. So shall I start from beginning again?
Yeah. That's what is a request from audience.
Okay.
And also try to be a
Fine.
little louder. Maybe.
Okay.
Yeah, maybe the connection is also not supporting, but yes.
Fine. Okay. So let me start from beginning. So this is, we are starting with a simple problem to demonstrate how quantum computing can be used to solve a practical problem. So it's called ship loading problem. There are many other such problem which can be solved using quantum computing. It's called optimization type problem. So there are two ships to be loaded with 10 containers. That's the issue. That's the problem. Weights of each container is given to us. So 1, 5, 9, 21. These are weights for each of the 10 containers. And we are supposed to load the two ships with these 10 containers. Is this better, Praveen?
Yeah, it's very much better. Yeah. Go ahead.
Okay.
Continue. Yeah.
Fine. So, so what we see is that even for this simple and trivial problem, if we have to evaluate what is the most optimum arrangement of container on two ships, there will be more than 30,000 combinations possible for us to check and evaluate and see which one is the most optimum in terms of loading the two ships, so that there is no overloading of any of the two ships, neither there is an underloading of two ships. Now, if you see a typical ship, more than from 500 to 25,000 containers can be loaded on the ship. So on the average, one ship can carry, 15,000 containers. So now we can imagine that, how difficult, how many combinations and how difficult it will be for any human being, or for that matter, even traditional computers, to find most optimum problem loading the ship. So this is a use case which what we'll do is, just to give you an introduction, I have given you this. At the end of this presentation, I will run a small program and I'll show you how quantum computing is actually solving it. So in the middle, we will talk about what quantum computing is about. So there are a lot of buzz about quantum computing in media. Many companies are working on it. IBM, Google, Microsoft, and many other companies. And I'm sure you have, come across such news and aware of that. Why do we as a project manager need to know about it? So this is a very recent uh, phenomenon, new technology, upcoming technology. We don't have direct use of this technology in day-to-day business yet, but the impact of this technology is so huge. It has potential to transform many industries, and it can solve typical optimization problems in various fields like finance, logistics, healthcare, etc. It also has impact on encryption and security. So it is important that we as a project manager are aware of this trend, so that if opportunity come our way, wherever we are working, if opportunity come our way, we can spot it and make use of it. With this as a context, how are we going to talk about quantum computing? So we'll talk about what quantum computing is very briefly. We'll talk about a bit of physics. We'll talk about a bit of qubit. So in traditional computer, we have bits. In quantum computer, we have quantum bits, which is called qubits. We'll talk about where does quantum computing industry stands today, what is the current state of quantum computers, and what are the typical use cases where quantum computing can be applied potentially. And in the end, after having covered this, I will we'll come back to the ship loading program. I will run a program and show it to you. So quantum computing is nothing but a computer which does certain calculations, certain computations, but it uses a totally different physical phenomena than traditional computers. It uses what is called superposition and entanglement, and few others physical phenomena at a quantum level, which is sub atomic particle level phenomena. It uses to does computing work. So we'll talk about a little bit of physics now, which is going to help us in basic understanding of what is quantum computing. So we all know that light is a wave. So this two simulations kind of demonstrate what light is. On the right side, you can see there is an electric field, there is a magnetic field. So E is electric field, B is the red one is magnetic field, blue one is electric field, and they are pulsating 90 degrees to each other. And it is giving an impression of something is moving, which is nothing but light. So light is combination of pulsating electric field and magnetic field. So light is a wave, we all know that. But we also know that light is a particle too. So there are some phenomena which can't be explained if we assume that light is a wave. So for example, photoelectric effect, if light falls on certain material with a certain threshold energy contained in the light, then electrons come out of the material and go outside, right? So this simulation tells us that light cannot be wave. A wave cannot kick electrons out of a material. Light has to be some sort of particle. So light is both wave and particle. So that's something very strange thing scientists discovered almost 100 years back. So if light is a wave, typically what happens is, if you see on the left hand side, there is a light wave being generated here, and there's a two gaps. It is called two-slit. So it's very famous two-slit experiment. When the light comes out of first slit, you can see another wave is created, and second slit, when light comes out, another wave is created. So now just after two slits, we have two light waves, and they kind of collide with each other or interfere with each other. So this phenomena is called interference, and because of interference, you will see on the wall at the rightmost side, bands are getting created here. So wherever the two lights coming out of two slits, they interfere in a positive way or constructively, a bright spot is created. Wherever the two lights interfere with each other in a destructive way, a dark band is created. So this is called two-slit experiment. This is also a very old experiment. Scientists did almost 100 years back. And this shows that light is a wave. But interestingly, what scientists also found is that instead of, if we do the same experiment, but use beam of electrons and not beam of light, so we just take an electron gun, assume an electron gun, and we start shooting randomly towards the two slits. So we can all, going by our day-to-day observation of the world, we can say that electrons is not a wave. So it should, when we shoot electrons from an electron guns on two slits, we should get two bands, right? On the left-hand side, if you see, we are seeing only two bands because electrons are going either in first slit or the second slit. But actually what scientists found was that it doesn't happen like that. What happens is on the right-hand side. So left-hand side simulation is not correct. This is not what happens. What happens is on the right-hand side. This is what scientists observed, that even if you shoot electrons on two slits, we get a very similar result which we see when we shoot light instead of electron. So that creates a lot of problem. So earlier we saw that light is a wave, light is particle also, and now we are saying we know electron is a particle, but now we are seeing that electron is behaving like a wave. That is why these interference bands are being created in two slits. So very strange, world it is. Light is a wave, but it is also a particle. Electron is a particle, but it is also a wave. And this is what happens at the quantum level. And this is what is being used in quantum computing. We'll see how. So what happens is we can, we don't know what electron is, frankly. It's a particle, wave, what is it? Nobody knows. There is no picture of electron which we can, put in front of us and say, hey, this is electron. But we can visualize, we can think of electron as a sphere, as a football, a small football, teeny tiny football, which is rotating. But actually, it's not a football, it's not a sphere, it doesn't rotate. Nobody knows what it is. But this is what we are going to visualize. So electron is a sphere which rotates, and it can rotate in two directions. Okay, it can rotate in plus clockwise direction or anti-clockwise direction. And names are given to these two directions. So first one is called plus half, second is called minus half, or you can call it 1 and 0. Basically, these two state of electron kind of tells us what is a bit. So if you think of a computer which has a bit which can store 0 and 1, electrons, the two electrons here, the two different state or two different rotation, can represent information in quantum computer. So then the question is, then what is the difference between quantum computer and normal computer? Quantum computer also has bit, it can store 0 and 1. And quantum computer also storing, 0 and 1 through a positive spin and negative spin of electrons. So what's the difference? The difference is that another phenomena, which is demonstrated by this famous example of Schrodinger's cat. So this is a thought experiment, not actual experiment. So Schrodinger is one of the leading scientists in quantum world. His equation, Schrodinger's equation, is pretty famous. So his thought experiment was that let's assume a box and let's put a cat in the box. And we put a small device which can kill the cat. So if you think of traditional physics, our day-to-day experience, after certain time, we will think that either cat is dead or cat is alive, right? If you open the box, you will find the cat either dead or alive because of the device kept inside the box, which may kill the cat or may not kill the cat. But if you don't open the box and you just let it be there, what happens to the cat? As per our day-to-day, experience or traditional physics, cat is either dead or alive, no matter what. You open the box or you don't open the box, just doesn't matter. Cat is either dead or alive. But in quantum world, as per Schrodinger's equation, unless and until we open the box and observe, cat is neither dead nor alive. And that is the most strange part of quantum world. We will not be able to think how it is possible, because cat will be either dead or alive, right? So this phenomena happens very frequently all the time at the subatomic particle level. So if you think of our previous slide, which is an electron, which can represent 0 and 1 by way of its spin, will follow this Schrodinger's cat phenomena, which is unless and until somebody observes this electron will be in some state which is a mix of 0 and 1. So here we say, unless and until we open the box, cat is neither dead nor alive. We don't know. Same way, here we say, unless and until we observe what is the spin of the electron, or whether electron stores 0 or 1, the electron will be in a neither 0 state nor 1 state. So this phenomena is called superposition, where the actual state of the electron is superposition of 0 and 1, somewhere in the middle. Where in the middle, nobody knows. Unless and until we observe, will not know. And when we observe, so we build some equipment to measure or observe, what is electron is storing, whether it is storing 0 or it is storing 1. Until then, we don't know. It is in superposition state. The moment we observe, it will either become 0 or become 1. We will not be able to measure the actual superposition state. We will measure only the final state. So this phenomena is called superposition of quantum particles. And this superposition is the key ingredient of quantum computing. So why it is key ingredient? The reason is that one single electron, which in a typical computer can store only 0 or 1, only 2 values. But because of superposition, this single electron can store infinite values between 0 and 1. So any value between 0 and 1 it can store by way of probability. What is that probability? So let's come to that. So we all know what is probability. I mean, if you have a coin which you toss 1,000, 2,000 times. Most likely half of that will be head, half of that will be tail, but not necessarily, right? And the more you repeat that experiment, the more equal head and equal tail will come. If you do this experiment only once or twice, you may not get them equally. But if you repeat them multiple times, you will get them 50-50 roughly percent. So this is probability. So this probability is applied here as well. So again, coming to superposition, because this is the key ingredient, so that's why I'm spending a little more time here. So one single electrons, which is storing any value between 0 and 1. What is that value? That value is probability. So when we measure the electron, what is the probability that it will measure as 0, and what is the probability that it will measure as 1? That probability is being stored in this electron, and that is the probability which can be any value between 0 and 1. Single electron or single bit in a traditional computer can store only 2 values, but 1 bit or 1 qubit, as it is called in quantum computer, can store infinite number of probabilities between 0 and 1. So it can store 0.1, 0.2, 0.3, 0.4, 0.11, and so on. So one interesting thing which we can use from quantum computing is 1 bit storing multiple things. Okay, so this is quantum computing is nothing but kind of combination of physical concept at the quantum level, which is very different than physical concept at our day-to-day life level, and concept of probability from mathematics. So with that, any questions so far, or I hope I'm clear. So let's talk about a little bit of qubit. Briefly, we already talked about it. So qubit is nothing but one single particle, let's say one single electron, which is in superposition state of 0 and 1. Because we are not measuring it, we don't know what value it is storing, but it is storing a probability of it being either 0 or 1. So this is called qubit, and mathematically it can be represented as a sphere. So as I said earlier, we don't know whether electron is a sphere or not, but we can think of it as a sphere. And from the center of the sphere, you draw a line to the peripheral of the sphere. So that line can be infinite, right? That length will be same, but angle can be varied, right? So using this angle of that line, mathematically, we can represent probability of that electron, that qubit, giving us 0 measurement or 1 measurement. So this is at the top of this sphere. This is called Bloch sphere. This is conceptual sphere, not real electrons. So at the top, if the line is at the top, that means if you measure the electron, 100% probability is that electron will give us 0. If the line is at the bottom, this point, then that means it is 100% probability that when we measure the electron, it will give us 1. If the line is somewhere in the middle, so for example, if you see bottom left this chart, this line is somewhere falling here, neither at top nor at bottom. So this tells us that there is certain probability of when we measure the electron, we will get 0, and certain probability that when we measure the electron, we will get 1. So depending upon what is the angle, probability will vary. So this is a mathematical treatment. Will not go into that. So you can see that this any qubit or any electron which represents a probability of falling into 0 or 1 is nothing but combination of 0 state, sorry, 1 state. This is 1 state, and this 0 state. of different proportions. So if you take this at proportion X and this at proportion Y and mix them, you will get a qubit. So just to summarize, because it's a little strange thing to conceptualize, a qubit is an subatomic particle, let's say electron, which is in superposition state of 0 and 1. We don't know whether it is having 0 or 1, but we know what is the probability of it falling into 0 or falling into 1 whenever we measure. Okay, before measuring, we will not know exactly what is happening. So this qubit is what is used in quantum computing, and using those qubits, various blocks or what is called gates are created. So these are some of the example of the gates, and each gate is represented by a matrix. It's a mathematical formulation. Will not go into mathematics of it. And using few qubits. So here the example is with 5 qubits, Q0 to Q4, using multiple gates. So this qubit is undergoing gate H. And then it is undergoing gate T and so on. This is called quantum circuit. A quantum circuit is being created, which does solve problem like ship loading problem, which we saw in the beginning of this presentation. So before we move on, we'll not go into detail of this, just one quick thing. So what is one gate? Let's take one gate as an example. So what one gate does is you create a qubit, okay? Using a programming language, you get access to a physical qubit, okay, which is already existing. Using another programming language statement, you make that qubit either 0 or 1. So it is like initialization. You convert it into 0 or 1. So 100% chance that it will be 0. After that, what these gates do is simply change the probability. So if we want 25% probability of 0 and 75% probability of 1, we can use a specific gate to achieve that. If we want 50-50 probability, then we can use another gate to achieve that. Or if we want 100-0 probability to get converted into 0-100 probability, just opposite of that, we can achieve that. So these are some of the gates. All they do is they operate on the probability. They change the probability of a quantum bit being measured into 0 and 1. That's all they do. And of course, which means practically, theoretically, we can have infinite number of gates, but there are some very special gates which are used very frequently, like, X gate. X gate is nothing but it just changes the probability, makes it opposite. So if you have 100-0 probability, 100 for 0, 0 for 1, then it just makes them opposite. It makes them 0-100 probability, and so on. So we have seen, a very basic definition of what is quantum computing. We talked about a bit of physics, particularly, a strange world of, quantum particles. And particularly, we dwelled upon superposition a bit, and how superposition is used to form a qubit, and how qubit is, different than typical traditional computer bit. So with that, let's go into, current state briefly. So interestingly, okay, so we'll address questions towards the end. So let's quickly complete this and then we'll address your questions. So there is a very famous algorithm called Shor algorithm. It was introduced way back in 1994 when all the advancement in this field was not even present. So what Shor showed that using a quantum computing algorithm, we can factor prime numbers very fast. So if you see a number, this is 864, it can be factorized into 32 and 27. So 32 into 27 and so on. Finally, you'll get 2 into 2 into 2 into 2 into 2 into 3 into 3 into 3. So these are the factors of this number. This factorization we have all done in our school days. But if you take very large number, then finding out all the factors of the large number is not very simple task. It is very computing intensive task. So if you see this red chart, if number of digits increases from 0 to 50 to 100 and so on, the number of operations, number of computing required to factorize that number. So let's say 200 digit number, if you want to factorize, you need 20 to the 25, operations to do that. And a simple way of looking at it is that, it will take billions of years using traditional computer, which is transistor based computer, to factorize a number. So this fact that it takes a long time to factorize a number is used in encryption and decryption. So if any data or any confidential information is being transmitted, if you want to encrypt it and you don't want anybody else to snoop into it, you use this basic phenomena of factoring a number to do that, because whoever wants to crack your confidential information, they will have to factor that big number, and it will take billions of years to factor it. But using Shor algorithm, using quantum computing concepts, he showed that it is very fast, this blue line. So it is almost independent of size of the digit. And that is why you'll see a lot of, if you follow media, if you follow quantum computing, you'll find there is some worry that, quantum computer can help people crack encryption. So why is quantum computing fast? Why is that qubit is fast? One example we talked about is that it can store probability almost infinite, right, between 0 and 1. But there is other way. What happens is, let's take this example of this maze, where you can enter from one end this side and you can exit from this side. Okay. If you want to find a path from here to some other place, you can imagine that there are n number of paths we have to try. Not each path will be successful. We may get stuck at dead end, and only one path out of thousands of paths will be successful in taking exit, right? So traditional computer, how it will solve? I'm very much trivializing the algorithm here. So the way traditional computer will solve is, it will try each path one by one, and it has to try n number of paths, and only in the end it will tell you that this is the path which will take you from entry to exit in this maze. What quantum computer does is that it has capability to try multiple paths at the same time. So instead of trying all paths one by one, quantum computer can try multiple paths at the same time. And this is how it becomes faster. So not only it can store infinite number of probabilities in one qubit, but also it can compute in parallel with very less number of qubits. And therefore it consumes less energy, because you don't need a huge computer to do that. And you also don't need huge number of qubits to do that. Few dozen qubits are good enough. But there are problems with quantum computing. So today we are in an era called noisy intermediate scale computing. So it's a noisy because what happens is, when we operate a gate on a qubit, it can hold the result only for a fraction of a second. And after that, noise kicks in, interference kicks in, and it loses the state. So any computing we do on quantum computing has to be done pretty fast. So it's noisy. We don't have, we have only few dozen qubits computer today. Okay, so we don't have thousands of megabyte and gigabyte kind of situation. We are not there yet. We have only few dozen qubits today. However, there are significant process made in last few years, and there is a risk that quantum winter may kick in, which means that like so what quantum winter term signifies is that we may hit a brick wall and progress will not be made for several years or several decades. So that is called quantum winter. So there is a risk that we may get into quantum winter and progress will not be made. But net, given all this problem, because of the potential of quantum computing transforming several industries, a lot of companies are investing in it. Some companies are investing in creating quantum computers. Some are investing in creating a platform for programmers to use, and some companies are exploring how to take advantage of quantum computing. So this is just a chart to depict how quantum computing has progressed by different. So these are different manufacturers of quantum computers. And so let's take one example, D-Wave. So D-Wave has 5,000 qubit computer available. So this is how the progress has been made. That's the only thing I wanted to show there. There is a Chinese company called SpinQ. So they have launched a portable quantum computer. It has only one qubit or 2 qubit. So it's a very small size quantum computer. A primary purpose is to teach quantum computing in schools and colleges, and it's pretty cheap as well. So few lakh rupees you can buy it today. It's already in market. But it's not for practical or official or business purpose, merely for teaching. Quantum computers we can access today as we speak on various clouds. So IBM, Microsoft, Google, AWS, all of these are offering quantum computers. So these all quantum computers are made by these manufacturers only. But what IBM, Microsoft, Google, and AWS have done is they have created a platform on top of the quantum computer, and you can use them with the program offered by these companies. So even quantum simulators are available. So because quantum computers, when you actually use them, it's costly. So when you want to write a program and you want to debug the program, you better debug it in a simulator with a small scale sample, right? So quantum simulators are also available where you can test the program, and once you are confident that it's working fine, you can run it on actual quantum computer with real data. There are already some programming languages available. For example, Q# is available on Microsoft Azure Quantum Platform. Qiskit is available on IBM Quantum Platform. These two, Qiskit and Q# are very widely used in the industry. Python is also used both Qiskit and Q# actually very well integrate with Python. So we come to the last but one topic. So last but one topic is what is a typical use case, and then I'll show you the program in action. So typical use case is various form of various form of optimization. So if you have a share market, if you can think of where you have, let's say you have 1 crore rupees from your customer and you have to build a portfolio of shares, let's say a portfolio of 10 shares, which will give a good return at low risk for that 1 crore rupees. So out of thousands of shares, what are those 10 shares which will give a good return at acceptable risk? So that's a problem to be solved. It is called optimization problem. And there are traditional techniques such as Monte Carlo technique, etc., which is being used, but those are approximations. Using quantum computer, we can solve these kind of problems. So that's why you will see finance there. In transportation, we are seeing one example right in this presentation, ship loading problem. But there are other problem also, which is called traveling salesman problem. How a salesman which needs to go to 10 places, what is the most optimum route for him to cover all those 10 places? There are use in medical and pharma, where if you have, let's say, you have a molecule and you want to find out how does molecule react to a particular substance. And the way typical pharma companies work, I'm not sure if there are people who are from pharma, they will know better. I'm not a pharma expert, but at a very high level, you experiment with thousands of molecules, and thousands of molecules need to interact. You need to check that they are interacting not in a harmful way with various chemicals present in our body, right? So how do we check that? So you have to perform actual experiment, which takes time, money, cost. So using quantum computer, you can simulate chemical reaction and see how a particular molecule reacts with a particular chemical in our body, not without conducting experiment in quantum computer, and so on. Cryptography, we saw that breaking cryptography can be done using the quantum computers, etc. So yeah, we talked about this chemical reaction modeling, how an enzyme, or even in fertilizer, how an enzyme, how it works in a fertilizer, drug discovery, etc. In optimization, multiple things like finance, investment portfolio, economics, etc. Similar to Monte Carlo simulation can be done. Grover algorithm is such. So this is another, we talked about Shor algorithm. Grover algorithms is basically you can do unstructured search using quantum computing. But there's something called data loading problem, which is not yet solved. So you have a quantum computer and you have a huge amount of data to be searched from. But today, what is the problem is that how do we load that huge amount of data into quantum computer? We can't, because we have very small quantum computer with us right now. So there are some problems which is not yet solved here. Factoring, we talked about encryption. So these are some of the use cases. There are many other use cases where we can apply potentially quantum computing. So we are coming back to ship loading problem. We have seen this at the beginning of the presentations. I'll just quickly, show the program in action. So just to give you a sense of, how it works. So this is a sample program. I'm using it. So I'm using Microsoft Azure, Azure's quantum computing environment, using Python and Q# language. And some of you who are familiar, this is Jupyter Notebook, Python programming language, and Q#. So we'll just quickly run this. This is ship loading problem. They have explained here. Actually, if you go to Microsoft or even Qiskit website, you will find plenty of samples and a lot of explanation, how it works, mathematics behind it, and so on and so forth. We'll skip these. We'll just run the program and see. So I'm running this program. So the same example, this is container weight, 10 container weight, which is to be distributed among 2 ships. So now it is submitting the problem to Azure platform. So this I'm running in my local machine, and it is now connecting to Microsoft Azure to submit the job to the quantum computer. So it asked for my authorization. It is now submitting the problem. Result has come, but it is unformatted. So we'll format that. So this is a formatted result. So it says container 0 with weight 1 was placed on ship A. Container 1 with weight 5 was placed on ship A. So these first 4 containers it decided to place on ship A. Then 3 containers it decided to place on ship B, and so on. And then finally it says, ship A has 52 tons and ship B has 53 tons. So this using quantum computing, we can see that now that 10 containers got kind of equally distributed between the 2 ships. There are a few others, further, there's something called cost function, which is further got optimized. We'll not get into that because result will be anyway same. So even if you have optimized. So I think I'm done, Tashin or Praveen. So we can go into
Sure. Thank you,
question
Amit.
answer. Yeah.
Yeah, definitely. We'll open the forum for questions. Team, please use the Q&A button if you can. The reason is we do not want to lose your question. I see great questions coming in. Amit, I'm just taking the control. Is that okay?
Yeah, please.
Okay, thank you. Let me just go full screen. Are you able to see any questions, Amit, on the
Yeah, I can
screen?
see many questions, but I think if you can filter out and tell me which question to answer.
Okay, just let me just check quickly. Okay, because I am able to see only 2 in the
Okay,
chat
fine.
earlier. So let me just quickly check if I have missed anything. Okay, so there is a question which is for algorithm. Somebody is looking to understand what is the algorithm used in this program. I believe you mentioned there are multiple, but if you can take it forward.
Yeah, this program is the one which I showed is not using any very standard algorithm. It's a very simple program which uses a very simple, quantum circuit to solve it. So you can say it's an optimization program here.
Okay. Mahesh, is your question answered? Please do let us know in the chat.
So there is one question: do we need to port existing software? Um, So I don't know what you mean by that. See, what happens is today's quantum computer will work in tandem with traditional computers. So as you saw the program which I demonstrated, we used sample computer, right? We used traditional computer from my laptop. And only one portion where the circuit is being run on a quantum computer, only that one line was executed on quantum computer. Rest of the lines which I showed got executed in my. So no, there is no porting of software is required. Typically, the way it will work is combination of both existing software in traditional computer in conjunction with quantum computer.
Thanks, Amit. There is another question, I think, sometime back that Sri Krishna has posted. He wanted to understand what type of hardware would make a quantum chip.
Okay, so So that's a interesting question. So there is no quantum chip in the way you have a traditional computer chip. So what you have today is, let's say, 12 qubit quantum computer. Let's take example of that. So all you have is 12 electrons in a lab, which are put in superposition. That's all. So today there is nothing like equivalent of chip today. And these 12 electrons which are in superposition require very low temperature, 0 Kelvin temperature to be more precise. So you can't move them around. They have to be there in a lab which can maintain that kind of environment, that kind of temperature. Plus, as I said during the PPT presentation, there are a lot of issues related to noise. So if you have a magnetic field near quantum computer or near an electron, which is qubit, it can interfere and create noise. So these labs which run this quantum computer have to be very heavily sanitized in terms of any potential interference from outside signals. So these are very costly affair. These are maintained by very few companies who can afford, that kind of environment. And they offer quantum computing through one of these cloud providers like Google or AWS. Okay, next, Tessie.
Yeah, so since you mentioned about separate environment or separate system for it, how are these containers, right? So how are these containers getting the information? Are they having any
So
sense?
there
Because
will be
are these
connection, yeah.
IoTs? Okay.
Yeah, so there will be, so yeah, it won't be IoT, yeah, but there will be connection from, let's say, Microsoft Azure quantum environment has connected to multiple quantum computer providers to actually submit a job and fetch the result back.
Okay, okay. And another question I remember you mentioned about like different industries that are leveraging quantum computing, but is there any company or any use case which is running within India?
Not to my knowledge within India. And the first assumption that our companies using quantum computer to solve real problem today, I really doubt. Of course, I can't answer that with 100% certainty, but I really doubt. So what is happening today is companies are investing time in finding out applicability of quantum computing today. So we are not in a state where we can say that, this use case really works great in quantum computer. No, we are not there yet.
Okay, okay. So the next one is on the how do quantum computing and supercomputers compared?
They are actually chalk and cheese. Supercomputer is still traditional computer, which is large in scale, lot of parallelism, and etc. Quantum computer, totally different phenomena it uses, as I explained. And if you take example of simulating chemical reaction, okay. Now, chemical reaction is a physical phenomena, we all know. And when you put a molecule with some environment, another chemical, some chemistry will happen in instant of time. But if you break it down and try to understand what is happening at quantum level when that chemical reaction is happening, it's very complex. So if we want to simulate this chemical reaction in a computer, whether it is supercomputer or normal computer or traditional computer, if you want to simulate it, you have to understand all that complexity and build that complexity in the program you write, correct? Whereas if you use quantum computer, because quantum computer, fundamental of quantum computer is those very phenomena which gives rise to a chemical reaction. So this fact is what is going to be used in quantum computer a lot, where we don't have to understand the full complexity of chemical reaction and still be able to simulate it in quantum computer. So you don't have to write very complex program, because at the base of the quantum computer is nothing but a quantum world, which also drives quantum computer and also drives your chemical reaction. Therefore, it becomes very beneficial where, without understanding the full complexity of a chemical reaction, we will be able to model and simulate a chemical reaction in quantum computer. So fundamentally, these two are totally different worlds.
I hope that answered.
Yeah.
And the thing that you're explaining, right, Amit, it's more like when you are writing code or when you are actually, um, you know, writing down your code you are using quantum
Mhm.
computing, right? How is
Mhm.
this, how as a project manager can I use it? Is it just that I need to understand it, how much effort will be needed and I need to use it for my
No.
effort
Yeah.
estimation?
Yeah, understood. So I think effort estimation is not going to come in picture in near future at least. So for a project manager, what will be good is that if you have um, awareness of the trend, if you know what is happening in quantum computer, what are the new advancements happening every day. So it's a hot topic. So every day you will get some new advancement happening. And having understood what are the strength and what are the weaknesses of quantum concept or quantum computer, you should be able to decide that, hey, this is a problem in my company. Where why don't we explore if there is a solution available in quantum computer? I think we are at that stage right now, not at the
Okay,
estimation stage.
okay, yeah, got it. And you initially spoke about AI analytics and all. Are these somewhere getting related to AI ML as well?
So at the underlying level, there are some algorithms which overlap between AI, ML, and quantum computer. But other than that, they are different concepts.
Okay, okay. Um, I do not see any other question. Did I miss anything? I think we are good. I think there are questions related to like manufacturing industry. How is it being used? I believe your one of the slides talks about it, but in case you
Yeah.
want to add anything.
Yeah. So to be frank, I'm not sure how it is being used in manufacturing industry. I guess if there is an optimization a problem within manufacturing industry, for example, I remember you will typically have um, scheduling of jobs on various machines. And so there used to be a software called I2 or I3 in the past, which was used to optimize job loading problems. So
Mm.
you are manufacturing, let's say, laptop. It's a laptop factory, and you have a demand for 1,000 laptops to be manufactured today. How do you load various machines in the shop floor to be able to optimally manufacture those laptops? So that's a kind of optimization problem, I guess, that potentially quantum computing can be used there.
Mm-hmm. Thank you. Thank you. I think we will wrap up with just one more question, which is this is my question as well, Amit.
Sure.
Somebody has asked about it. Like in my B school, right, I have read in supply chain and optimization where we have used linear algebra to solve
Right.
this problem, right? So
Yeah.
how is this different from linear algebra versus this quantum computing?
Okay, so linear algebra is, the first method of solving any problem, not only optimization problem, but any other problem which can be modeled using linear algebra. We can solve that. But what happens with linear algebra is, number one, not all things, all phenomena, all happenings are linear in nature. Okay, so for example, okay, you have the PPT, so I can't show it. So I showed one of the slide where,
Do you want me to?
no, that's fine. That's fine. Let me
Question?
explain.
Okay.
Yeah. Anyway, we are at the end of the session, so they're not all phenomena are linear phenomena. So there are logarithmic phenomena, and then quadratic phenomena and polynomial phenomena. So they follow different equations, not just linear equations. So that's one problem with linear algebra. Having said that, so when you talked about, you all have learned, using linear algebra solving
Right.
optimization problem. What we are doing with quantum computing is solving optimization problem, nothing else. It's same thing, just that we are solving optimization problem where linear algebra cannot be used because number one, problem is complex. Number two, when you make the problem scale up, so for example, instead of 10 container, use 15,000 container. It's a very huge scale. Then linear algebra becomes problematic. It takes long time. Or when the fundamental nature of that problem is not linear, so you can't apply linear algebra there. So there are a lot of situations where linear algebra cannot be used, but you are right, it's a very good connect that, the way we have solved optimization problem during our school days and college days, quantum computing is doing exactly same, just that much more complex problem, much more faster.
Okay. Okay. I'm sorry, I think. Yeah. Great. Thank you so much. This really helped. I believe, we have answered all the questions. Thank you, Vishnuvardhan. So next is, as we all know that, as Mr. Bill Gates also said, we all need feedback so that we can improve upon. Please use this QR code. And if you need this tiny URL, I can just copy paste the tiny URL. Please, while you are here, please give us your feedback so that we can improve upon going forward. And just copy pasting the URL here. I'll just give you like 3 minutes. Amit, please stay on.
Sure, yeah.
Indeed, Gokul. We look forward for your candid feedback. Please do provide us with. Please do let me know on the chat if you're done. Thank you, Prateek. Yeah, while you are on feedback, let me just tell you, Amit, when you started off and I looked at the subject line, I was wondering, what topic it is and how is this.
Okay.
When you started, even I was thinking I'm going back to my physics class in the college. And
Sure.
I was thinking how I'm going to use it. Like, initially I
Okay.
thought maybe just for the people who are in maybe logistics department, but when your slide came up on the use cases and its applications, right? So I was wondering, I have a background in marketing. So when I looked at it, you mentioned about customer and all, right? Like advertising. I was surprised to know that it's being used in advertising. Maybe I will do more of Googling on that and try to see if I can find something, how it is being implemented, or how the application is in marketing.
Yeah.
Thank you for
Uh,
that. That's an eye
Harshin,
opener.
Sorry,
Yes,
Tessin.
Gokul?
The link that's been posted on the chat window is actually of a YouTube link. It's not a.
Oh, really?
Feedback link. Yeah. Can you post the
Okay.
feedback link in the chat
Uh,
window?
Okay, just a moment. Let me just quickly check. Thanks for calling it out. Can you check now, please?
Yeah, I think it has come.
Okay, thank you.
Yeah, thanks, Yassine, for organizing, and thanks everybody for coming over here on a weekend to join this session. I hope it was fruitful, and you will carry this back to wherever you work, and you will be able to apply some of it. That will be great outcome if you are able to use this session for benefit of your organization.
Thank you, Amit. You have taken some of my job. Thank you so much for thanking everyone. Definitely, I feel personally, even though I had no idea to begin with, but this really helped me. At least it's an eye opener for me. The cloud offering that you mentioned, right? I was not aware of. Thank you
Okay.
for that. And the members, whoever is a PMI membership, who has PMI membership, will get one PDU automatically credited. In case you have not shared the PMI membership ID with us while registering, please write us on the events at pmipcc.org, and we will be able to help you out. Thank you so much for joining, and thank you, Suma, for helping us connect with Amit for this wonderful session. Thank you, Gokul. Thank you, all the participants, on joining us on our weekend. Thank you so much, and looking forward to see you again in the next session. Thank you, Amit.
Bye.
Thank you
Thanks a
all.
lot.
Bye.
Bye.